We are beginning my favorite part of the course, which is antiderivatives and integration. But before we do, I want to remind you of something that I mentioned in our exponential function day, and that was a of t, and we thought of this as an amount at time t. A of t is a constant c times e to the kt, that this function satisfies dA dt is k times a, and I call this a differential equation. And well, generally a differential equation is, well, it's an equation that gives a relationship among a function and one or more of its derivatives. And here, this giving an explicit formula for this function is a solution to this differential equation. And moreover, this is what's called a general solution. It's all solutions are of the form of constant times e to the kt. Well, if we now talk about antiderivatives, we can frame this in the language of differential equations. So an antiderivative, I'll start this way. I'll say given f of x, an antiderivative is a solution to dy dx equals f of x. And this is one of the simplest types of differential equations. Well, I will just add, many of you will go on and take courses where you study much more involved differential equations. It's a beautiful subject, but this is what we study with Calculus 1, Calculus 2. So an antiderivative satisfies dy dx is little f. What does that mean? It means I'm handing you the derivative f of x. And the answer, which would be an antiderivative here, is what would be the original function. Another way to say this, equivalently, capital F of x is an antiderivative for little f of x, provided capital F prime of x is little f of x. So this here is saying the exact same thing. It's just not written in the language of differential equations. What if we wanted the general solution to this differential equation, or the set of all antiderivatives? So the set or collection of all antiderivatives for some function f of x is, well, you take 1 and then you add plus c, where capital F prime is little f and c is a constant. Now you can think about this really. We know derivative of constant is 0, and so this thing, capital F of x plus c, will certainly have the same derivative as just capital F of x. Now I'd like to get into its part definition and part notation. What I'm defining is what's called the indefinite integral. So let's talk about this. I'll write it big. This equation means capital F prime of x is little f of x. Now, let me start labeling some things. This big elongated s is called an integral sign, or the integral sign. F of x is called the integrand. This dx, this is the differential. It tells you the variable. And what you see on the left-hand side, this is here. It's an indefinite interval. And every interval starts with an interval sign and ends with a dx or d, whatever your variable is. And the verb here is where we integrate f of x. Just like if you said d dx and then wrote a function, we would be differentiating. Here, with the interval sign, integrand dx, we are integrating. And then over here, this is the set of all antiderivatives. And this is what an indefinite interval is. It's a capital F of x plus c, and it's a collection of all antiderivatives. And to write this, this means capital F prime is little f of x. And so we will calculate a few indefinite intervals just by thinking about derivatives. But then we will get into some formulas. So most rules we know for derivatives, they correspond to rules for antiderivatives. Okay, so let's see a few examples now. What would the interval of 0 be? Well, ask yourself, what function has derivative 0? It's just a constant. So the interval of 0, dx, is just the constant. It's c. Another one, what about 1? dx. We integrate 1. What function has derivative 1? X. Okay, so be x, but then plus c to get all antiderivatives. Let's see, how about 2x dx? What function has derivative 2x? X squared. Okay, so this would be x squared plus c. And typically how we solve indefinite interval problems is you need to think of one antiderivative. And here I'm really thinking, but we will have different rules and techniques. And then you put up plus c like this. So let's do just a few more. What about 3x squared dx? Well, what function has derivative 3x squared? This is x cubed plus c. Finally, oh, here's one we can do. It doesn't fit the same pattern, but what about e to the x? The derivative of e to the x is e to the x. And so when we integrate, we also get e to the x plus c, because just differentiate this on the right-hand side and you get the integrand. Okay, so these are all really great examples that we thought of just by thinking about what function has this derivative. Now, let's move right into our first rule. It's called the power rule. That when we were first learning derivatives, the first rule we learned was the power rule, and similarly here. Well, what does this say something about? We integrate, say, x to the p dx. When we're differentiating, the power rule is bring down the power, x to the power minus 1. This will clearly be a different rule because we are going the other way, we are integrating. But just thinking about it, if differentiating has a power minus 1 in the power rule, when we integrate, part of what we will see is a power plus 1 in the power rule. So this is, we add a power, divide by the higher power, plus c, okay? This is the power rule for intervals, indefinite intervals here. And you can check, right? Differentiate this, and you get exactly x to the p. And as a quick example of this power rule, let's do x to the 100 dx. It's a power rule. So we add a power, x to the 101 divided by 101 plus c. Now, stare at this rule for a moment before we do anything else. Does this hold for every single p? I hope you say no, because look, if p is minus 1, this would say x to the 0 over 0, and we know we can't divide by 0. So this is only for p not equal to minus 1. Okay, as I mentioned, if you try to use the power rule, where could I write this? Maybe at the very bottom. The integral of x to the minus 1 dx is definitely not x to the 0 over 0 plus c. This is not anything. This would say 1 over 0, which is not anything. So just be careful that you don't use the power rule when you have x to the minus 1. Here are 2 examples that use power rule, or we also see an e to the x here. So first of all, let's talk about this. We have a sum of 3 terms. You know to start an integral because you see an integral sign and it ends when you see a dx. So the function, the integrand, is these 3 terms. You might also see parentheses here, and that's perfectly fine too. And similarly, this has 2 terms you might see with parentheses. Okay, let's get started now. What do you think happens? We have a sum of 3 terms or a sum of 2 terms. Well, if we were differentiating, we would differentiate the first term, put a plus, differentiate the second term, put a plus, etc. And this is what we do with integrating also. And just like derivatives, if you have a constant times a function, well, we write the constant down and then times an antiderivative for that function. Okay, so this is linearity of the integral. How does this work here? Let's work through these 2. Well, term by term, we write down the 2. And then this is x to the 3rd power. We add a power, divide by the higher power. Then we put a plus, write down the 2/3. This is x to the 6th over 6. And then we put a minus, and then we integrate e to the x. So I integrated term by term, and then at the very end we put one big plus c to get all antiderivatives. And if you want, you can write this as 1/2 x to the 4th power plus, let's see, this would be 1 over 9 x to the 6th power minus e to the x plus c. Okay? Now, in the second problem, both terms are power rule, except we don't see the powers exactly like this. But if you remember when we first started differentiating, we can take this initial step to write each one of these as x to a power. So this is 2x to the minus 2, and then this is x to the 1/2. Okay, so now I integrate term by term. We get 2, and then add a power, divide by the higher power. Okay, power rule. And then we add a power, divide by the higher power, plus c. I don't really like to leave fractions in my denominator, so let me clean this up a little. This is minus 2 over x. This is plus 2/3, x to the 3/2, and then plus c. Now, one thing that you can always do is when you're integrating, you can always check. So you could take this underlined in blue, take the derivative, and you will get this integrand. And similarly, take this underlined in blue, take the derivative, and you will get this integrand. That's the relationship between, well, integrand And here, the indefinite integral. Here is my next example, but I will caution you that you have to be careful, because while you might think you can rewrite this as a power, and you certainly can, it's 6x to the minus 1. Remember, the power rule does not work for x to the minus 1. This is definitely not x to the 0 over 0 plus c. The power rule fails on this term. So before I do this example, what is this integral? What is this? Just think to yourself, what function has derivative 1 over x? Well, you might say ln x, but for antiderivatives, we take ln, absolute value of x, and then plus c. And you might remember, we did this in class, the derivative of ln, absolute value of x, is also 1 over x. But by putting the absolute values here, this function, the integrand, and this function, its antiderivative, they have the same domain. And so this is what we take for the integral of 1 over x dx. ln, absolute value of x, plus c. Okay? So now let's return to this specific problem. We have 5. We add a power, divide by the higher power. Okay? And then plus, well, if the integral of 1 over x dx is ln, absolute value of x, this would be 6 ln, absolute value of x. And then we put 1 plus c. And I will just leave it like this with a 3.2 in the denominator. So here is the indefinite integral, or all antiderivatives for this function here. Now let's discuss these 1, 2, 3, 4, 5, 6 antiderivatives, or indefinite integrals. And these are all ones that I personally just have memorized, but the reason I have them memorized is because I remember the corresponding rules for derivatives. So let's start with these two, sine and cosine. We know the derivative of sine is cosine. Immediately that tells us this one, that when we integrate the cosine, we get sine x plus c, because, well, I was just saying, differentiate this, and you get the cosine. Now here, the derivative of sine is cosine. The derivative of cosine is minus sine. And so here, we don't just put cosine, we put minus cosine x plus c. And now check, right? If you differentiate negative cosine, we get negative of negative sine, which is positive sine. And I would say these two are ones that people mess or confuse the SIGN sign, because it's sort of the reverse of what you see when you're differentiating. So the integral of sine, negative cosine. The integral of cosine is positive sine. Okay, these two are probably two of the most important on the board. And then secant squared, what function has derivative? Secant squared, it is the tangent. Here, what function has derivative? Secant x, tangent x, this is the secant. Okay, those two kind of are in a pair. Now these two are also in a pair. These are inverse trig. Well, once we integrate. Here, what function has derivative? 1 over 1 plus x squared. This is the tan inverse, or arctan. This one comes up a lot in calculus 2. Finally, what function has derivative? 1 over square root 1 minus x squared. This is the inverse sign. So these are 6 antiderivatives or indefinite intervals that I always remember because I know their corresponding derivative rules. Now let's do some more examples. In the first problem, we see a sum of 2 terms. The first term, this is 4 times an antiderivative for 1 over 1 plus y squared, which is the tan inverse of y. And then here, when we integrate sine, we get negative cosine plus c. So this is the answer for the first problem. So maybe I will rewrite the first term. This is the integral. It's t to the negative 1/2 plus 2 over square root 1 minus t squared dt. And now I'm ready for the power rule. We add a power, divide by the higher power, and then we have plus 2 sine inverse of t plus c. And then finally, I would not personally leave a fraction in the denominator. You can write this as 2 square root t plus 2 sine inverse t plus c. Here are 2 more great examples. You might think product rule, quotient rule, but we're not going to get into that this semester. Well, I will comment. There is a corresponding integration technique that comes from the product rule for derivatives. It's called integration by parts, and this is how we begin calculus 2. But even this, I don't think I personally would do that way. We can, in both of these, we can use algebra first before we integrate. So here we can just multiply through. This is an x to the 3/2 power plus 5 over x, just multiplying through by x. And this one, well, I can break it into a sum of 3 terms. We would have x is the first, 5x to the 4th over x squared is 5x squared, and then we have a 7 over x squared, which I will write 7x to the minus 2. So both of these, as I mentioned, we took a step to simplify the algebra before we integrate. Here, add a power, divide by the higher power, and then this is not power rule, this is ln absolute value of x. So we have 5 ln absolute value of x plus c. And here it's 2/5 x to the 5/2 plus 5 ln absolute value of x plus c. So here is the set of all antiderivatives for this integrand. And now let's do the second one. Well, we integrate term by term. Here, this is x squared over 2 plus we have 5, and then x cubed over 3. Add a power, divide by the higher power. And finally, we have a 7x to the minus 1 over minus 1, which we had a similar antiderivative not too long ago. It's minus 7 over x, like this. Okay? Here is a great example, and it's a little bit different than what we have done before. Suppose we have a particle, and this is motion along a line, and it has velocity. D of t is t plus cosine t, and its initial position is 5. So we're given this velocity, initial position. We want to find the position function, p of t. Now, maybe here, let's talk about this for a moment before we jump into the problem. We start off with position, P of t, position, V of t, velocity, and A of t, acceleration. And there's a relationship which we have discussed from very early in the semester. Going in this way, we take the derivative. The derivative of position is velocity. Derivative of velocity is acceleration. Okay? Now, if we go this way, this is taking the antiderivative. So we integrate acceleration, we get velocity. We integrate velocity, we get position. Okay? Because of this relationship. But it's more than that here. We will not have position as some function plus c. That would be all antiderivatives. And you see, we don't want all antiderivatives. We want a specific antiderivative. Of velocity. We want the one that satisfies P of 0 is 5. First, as I mentioned, we integrate velocity. This is the integral of t plus cosine t dt. This is t squared over 2 plus sine t plus c. This is all antiderivatives, or this would be all possible position functions that have this velocity. But we want P of 0 equals 5. I'll say where P of t is this, t squared over 2 plus sine t plus c. And so let's evaluate P of 0. If this is P of t, 0 plus the sine of 0 plus c. The sine of 0 is 0, and so P of 0 is just c. But then here we want, or here, P of 0 to be 5. And so this tells us the constant is 5. Altogether, we have the final answer. This particular antiderivative is t squared over 2 plus sine t plus 5. This would be the answer here. Let's do one more problem of this type. We want to find the antiderivative, capital F, of little f, where little f is 1 over x plus 1 over x squared plus 1. And here, capital F of 1 is 0. This will specify a particular antiderivative. Okay, first of all, we start by just integrating. We get ln absolute value of x plus tan inverse x plus c. But then we want, so maybe I'll write capital F of x is this, ln absolute value of x plus tan inverse x plus c, where capital F of 1 is 0. This is what we're looking for. So we set 0 to be, now I evaluate this at 1. Natural log of 1, 0. Tan inverse of 1. Oh, this is a very nice problem. This says the tangent is 1, and the angle is between minus pi over 2 and pi over 2. Tangent being 1, it happens where the sine and the cosine are equal, and the angle is theta equals pi over 4. Okay? Here we get pi over 4 like this. Now you see, in this case, c is negative pi over 4. And so the final answer here, capital F of x, ln absolute value of x plus tan inverse of x, and then minus pi over 4. This here is our final answer. I'd like to end today by really just having a discussion. So what do we know about derivatives? Well, I have, either in class or you have worked on, some really complicated things. Functions that involve product, quotient, chain, maybe sine, and a 2 to the x. Sort of all combined into one, and we can, provided we are careful, we can differentiate. But the same really is not true for integration. What I have on the board is 6 integrals, and they are organized by row. The first row, you see, they're all kind of similar. We see powers of x. And the second row, they're all kind of similar. We see e to the x in it somehow. But each row has the property that one of the 3 integrals we can do right now. One of the 3 integrals we can do next time, so it's still Calc 1 material, and one of the 3 integrals we can't do. It's what's called, it has no elementary antiderivative, which means you cannot write an antiderivative as a finite sum of functions that we know. So let's see which is which in each row. First of all, for the ones we can do right now, this one, this should jump out at you as something that we can do right now. It's a sum of 2 terms. This is x to the 4th over 4 minus 2x plus c. So this is one we can do today. In fact, we did just now. And then if we look in the bottom row, the one that should jump out at you as being able to do right now is this one. Okay, we integrate e to the x, we get e to the x, and then here we integrate 8x. We're going to have 8x squared over 2 or 4x squared. And this one we do today. Okay? Well, now there's 2 left in each row, and 1 in each row remaining we will do next time. So I'll just say it's this one. This uses what's called substitution. And this is next time. And in the bottom row is this one. This uses substitution. This will be next time. And in fact, next time I will do both of these integrals just as part of our substitution day. So that means what's remaining, this integral, square root 1 minus x to the 4th power, and this integral, e to the minus x squared. Both of these we cannot integrate. We can't integrate now, nor Calc 2, nor Calc 3, nor any other math class, not with writing it as a finite sum of functions that you know. So this here has no elementary antiderivative. And similarly this, we have no elementary antiderivative. And I think this is an important comment and observation to make because this is fundamentally different than when we take derivatives. Integrating, not only do I consider it more challenging, but it's also some very simple looking functions you just can't integrate.